This is demo 2, demo week 2, which is week 7. So this would be week 7 of Math 211, and it's video 2. Okay, so now we know we have a polynomial. What fingerprints show up in calculus? I'm calling these fingerprints. So remember what a polynomial really inherently is a collection of roots, and some of those roots may be double roots or triple roots or complex conjugate pairs. That's essentially its fingerprint. And then what shows up in calculus? So let's start with a basic scenario, okay? I'm going to have some kind of polynomial here, and here's an axis. I'm going to make 5 little tick marks in each direction, maybe 6 or 7. Here's 5. 1, 2, 3, 4, 5 in each direction. Okay, now I'm going to have single roots here and here, and at 3 I'm going to have a double root. Let's see, I'm going to have at -3, I'm going to have a single root, and at -5, I'm going to have a double root. Okay, so that's my little symbol to remind myself. I'm going to try to draw this thing nicely. All right. There we go. All right. So basically, if I had an original function f, I'm going to estimate what f prime and f double prime are going to look like. Now, my little artistic comment here is there's certain things that happen in real polynomials that don't happen in artistic polynomials. So for example, when we calculate out an example later in class, we'll find out that, you know, the max in between two roots is not always going to be right in the middle. But we just kind of draw it that way. You know, it's going to be somewhere near there. It may be pushed off a little bit to either direction, but for artistic purposes, there are certain things we can do that are just, it's just okay. It's just totally fair game when you're doing some kind of approximation. One thing you can do, for example, you could always make these little lines cross, you know, these curves cross the axis at 45 degrees when you don't know what the angle is. I mean, that's totally fair too. So there's a lot of little artistic conventions that are fair game, but something you need to know is if there's some kind of symmetry in the problem, you want your curve to be symmetric. Things we don't worry about is, you know, exactly the angle of crossing the axis here, or exactly how high this guy goes or that guy goes. We don't care about things like that. Okay, we look at the basic behavior of the curve. We want to know when it's positive and negative, concave up and down, on average. We want to get a good idea of what it looks like. Okay, so again, we want to get the sort of the heart of the function. We're not necessarily picky about certain kinds of specifics. Okay, so my function has zeros at 1, 3, -1, -3, and -5. Okay. Now, let's see what will happen to f prime. Well, if f, you think about this little car driving along with a ladder on his head, and, excuse me, right, I thought I had to sneeze. Okay, so I've got this little ladder here, and when this ladder is completely flat, that's a max or a min point. There we go. And if it turns around, but it's on the axis, it's still a max or min point, right? Okay, I think that's it, right? So now what I'm going to do is I'm going to say in between two of these little red points, in between a max and a min, it has to either be strictly increasing or strictly decreasing. So I'm going to put little x's on the axis to indicate the derivative has to be 0 there. And then I'm simply going to do something like this. Let's just take, you know, two of these points. Like there's one at 0 and one roughly at 2. Okay, this function is strictly increasing, so this derivative has to be strictly positive. Okay, this other, where the car is sitting, all the way downhill, that's all going to be sloping downward. So there we go. Just sort of make a little hump there. Let's see, from about 2 to 3, this curve is decreasing, so the derivative has to be negative. And then finally, our final behavior is the curve is going up. You know, I don't know if it's going up like that or going up the way I drew it, but either one is close enough. Let's just keep working backwards. Okay, from -4 to -3, it's strictly increasing, so this is above the axis for the derivative. From -5 to -4, it's decreasing, so it's below the axis. And let's see, we're increasing from -infinity to -5. So there we go. This is the way it's going to look. And you think, oh my gosh, what a mess. Well, it is a mess. So I'm on a tablet, so I can do this. I can just separate these two, and I can make this f prime, and I can just kind of, I can just erase the stuff I don't want. I'm going to erase the blue stuff, get it out of our hair. I don't want this car either. Okay. Okay, so this is what f prime looks like. Okay, so maybe you don't want the f prime in the previous picture. So it's slightly easier to see. Okay, so now you see what f looks like and you see what f prime looks like. Well, maybe we want another derivative. Okay, we just do the same thing again. We just make another copy of this guy. There you go. Alright. Sorry about that. Is anybody actually watching these videos? Okay, there we go. Alright, now I'm going to make f double prime in green, and I'm going to do exactly the same thing I did before, only now I'm going to do this with between the red curve and the green curve. Okay, every time the red curve has a flat spot, I'm going to put a green mark down on the axis to tell me that the derivative is going to be 0 there. Right? And I'm going to start somewhere in the middle because it's just easier to see. Right, so from here to here, for example, I'm strictly increasing, so I have a positive derivative. Then between here and here, I'm strictly decreasing, so I have a negative derivative. Eventually this guy goes positive. Right, from here to here, it's decreasing, so this curve is negative, positive. And what do we have here? It's the red curve is decreasing, so it must be derivative is negative. Right? So I'm going to get rid of this red curve now. You don't mind if I get rid of the axis? No, just kidding. Alright. There we go. Try to clean it up just a little bit. Best I can so you can see it. Okay. There we go. There's f prime. F double prime and f single prime. Alright. We can see them right there. F double prime, f single prime. Just wiggle, wiggle, wiggle. Okay, that's all they do. Alright, so how do we plot polynomials using calculus? So the sheet that I have uploaded to Blackboard for you has 4 copies of the same, little cheat sheet. That's because I printed off in my class and sliced it up into 4 pieces. So that's why there's 4 of them. Okay, you only need 1, but they'll print all 4 of them because they're all identical. That's okay. You can use them as bookmarks, I guess. Okay, how do we plot polynomials? Actually, any function. But usually what we're going to be plotting is polynomials in this class. Okay, using calculus. Okay, So first of all, I'm going to say step 0 is plot any zeros if the polynomial is already factored. The reason I'm putting it as step 0 is because whenever I make lists of things to do, I never think to put it on the list, because it's one of those things that should be so obvious that you should automatically do it without thinking. Okay, but if you need to put it in the list, put it in the list. Okay, then of course it's a calculus class, so you want to take derivatives. So take f prime, and then you want to set f prime equal to 0, find x's. Now I'm calling it f and x, but really what I mean by x is your independent variable, and what I mean by f is the name of your function. So you could swap these things out obviously for any name of any function. In step 2 here, we're going to call these guys critical points, so we can refer to them later. Okay, I'm less concerned about what you call them, I'm more concerned about what you do with them, but we won't have any common language to discuss what we're doing if we don't name them something. Okay? Put the critical points, these x's, back into f, not f prime, to find the y coordinate. Alright, so this is going to allow you to plot these guys on a graph. Okay. Step 4, we're going to take the second derivative, and then we're going to set it equal to 0. Find more x values. And you're not necessarily going to call them critical points. I'm going to call them potential points of inflection, or PIs. Potential points of inflection. So they're not always going to be points of inflection. But if it is a point of inflection, it will show up in this list, but not the other way around. So it's a potential point of inflection. Okay? Now you're going to put these x's, these potential points of inflection, these are going to go into f. Again, not f prime, not f double prime. We want to find y values. This is so we can plot these guys. Okay. See if you need to calculate f of a and f of b. You don't always need to do this, but if you're plotting from, say, -4 to 7, you want to know what f of 4 is, and you want to know what f of 7 is. Okay? And you can make a little chart to keep track of all your data. Everything you've found, all your findings. And this chart can take different formats. I mean, every textbook author has their own way of doing this. But you want to classify, the important part is you want to classify max, mins, and points of inflection for all critical points and potential points of inflection. So you have a collection of x's that you got from both of those stages. You sort of bring them all into one big hat, and then you just classify them all. So if it's going to be a max or a min, it had to show up in the list of critical points. But there can be critical points that slipped in that were actually points of inflection. But then they will also show up in the second level. But you see, I can trick you. I can just say y equals x to the 6th. And you'll have a huge stack of zeros, which means huge stack of, first derivative is 0, second derivative is 0, down for quite a while. You can have the derivatives be 0, 0, 0, 0, and it doesn't necessarily give you any insight into whether the thing is a max or a min or a point of inflection. Okay, so there's different tricks we use, and as we continue the study of calculus, you'll learn more tricks. But the best trick to use in a pinch is just test a little value very close to the point that's to the right of the x value and another point that's to the left of the x value, and that's one way to get out of that jam. If you get a stack of 0, 0, 0, 0 derivatives all in a row and you don't know which way it's going to end up going, just poke at it with a calculator and see where it's going. I mean, that's all that a graphing calculator does anyway. Okay, so you want to know signs of f prime and f double prime at critical points and potential points of inflection. Okay, great. What else? Great. 9. And here's something I like. Carefully, of course carefully, plot what I call guiding points. And here's what I do. I plot, if I don't know anything about the point except I know where it is, I just make it a point. But if I know the point and the slope, I just say, well, is it pointing up? Is it pointing down? Is it flat? Okay, if I know something that's happening at that point, I put a little guide mark. If I know it's a min point, I sort of draw this kind of shape. And if I know it's a max point, I kind of draw this kind of shape. So then when I'm done, I can put them all together. Just as an example, what about if I have a point here, something like this, and maybe down here I have this kind of thing going. You know, I could connect the dots now, right? I can say, well, this is increasing over to here, and now it's going down like this. It's going to turn around. You see, connect the dots is more fun when you have more information at the point. So here, I don't have any derivative information here, so I don't know if it bends around, crosses through, or does something weird here. I have no idea. Okay. Okay, so then you just connect the dots. Okay. Now one last thing before I end this video is that not all steps have equal weight. You know, you don't have to use each step every time. You know, okay, so the whole point is, like I told my class, I said, there's not really any rules about graphing, like, oh, this is a list, you have to do blah, 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 and this is a procedure, and you have to memorize these procedures. That's not the way I want you to think about it. The way I want you to think about it is, you have a responsibility to make a mature decision about what's important in this polynomial or in this other graph. And here are some tools at your disposal that you can use to poke at it with. And it's your responsibility to choose the tools that fit the job. So for example, up here, I made this, rule number 0, or idea number 0, is to plot the zeros if the polynomial is already factored. Well, if the polynomial isn't already factored, or it's really, really difficult to factor, then you just don't do that step. Okay? Do you have to take the derivative? Well, usually, not always. Sometimes you need to take the first derivative, set it equal to 0, and find the critical points, but maybe you don't need that step. Or maybe you do take the second derivative, but you get enough information from just taking the derivative that you don't even bother going to the next step. You have to use your own judgment to figure out which of these things are most important. Okay? And so, you know, your experience will guide you. Okay? And, well, I will see you on the next video.